Okay guys, here's just a refresher on chapter 13, which is basically a review of the stuff that most of it you should already know. Some of it will be new, but just towards the end of this video. Okay, I've said discrete random variables, a variable which cannot be predicted in advance is a random variable. So something that's completely random, you don't know the outcome. A discrete random variable can only take exact values. So it's not continuous. By continuous, I mean, if I said to you, what's the amount of time it's going to take you to do a puzzle, and if I said it's between 0 and 1 minute, it could be anything between 0 and 1 minute, so that would be continuous. But if I said to you, how many heads would you get if you flip a coin? You could get, like if you flip a coin once, you could get 1 head or no heads. If you flip it again, you could get 1 head on the first, none on the second. You could get none on the first, 1 on the second, or you could get 1 on both, or you could get 0 on both. They're all discrete outcomes because the number of heads that occur is either 0, 1, or 2. It's not continuous, like you can't get half a head. So a discrete random variable is something that takes a specific value and has a probability. There's a probability of it occurring. Where are we? I wanted to change this to skinnier. Okay, so a set of favorable outcomes is called an event. So if I flip a coin twice and I say, what's the chance of getting 1 head out of those 2? Your favorable outcomes would be head, tail, or tail, head. All possible outcomes is called the sample space. So the possible outcomes that I can have if I flip a coin twice, my sample space is tail, tail, head, tail, tail, head, head, head. So they're my possible outcomes. So if I ever want to work out a probability, it's going to be an event over the total number in the sample space. So if I said, what's the chance of getting 2 heads? I would get 2 heads once. So the probability of head, head, it happens once out of 4 times. So the favorable outcomes over the total number of outcomes, or the number in the sample space. So let's have a look here at 3 coins being tossed. We want to see our possible outcomes. We could have a head and a tail. After we get a head, we could get a head and a tail, and if we get another head, we can get a head and a tail. Likewise here, head, tail, head, tail, head, tail, head, tail. Draw a tree diagram and hence list the sample space, so we can get head, 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 tail, head, tail, head. So what I'm doing is I'm following each branch to work out our possible outcomes. Head, tail, head, head, tail, 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 head, head, tail, head, tail, 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 head, tail, tail, tail. And you can see here we have 8 outcomes. That's because we have 2 here, by 2 here, by 2 here. 2 times 2 times 2 is 8. So we're going to have 8 outcomes. If we had a tree diagram, which was 3, and then 3, and then 3, we'd have 27 outcomes. So your number of outcomes is basically the number of things that you have on each branch multiplied as you add extra branches. Number 2, enrollment records show that the local school has 800 students, 450 female, 350 male. What's the probability that a randomly selected student will be female? So the probability of female is the number of females, the event, 450, out of 800, which is 45 over 80. We know that 5 goes into that 9 times, and into 80 16 times. So that's our chance of choosing a female if we pulled someone randomly from that 800 students. Okay, here's a few definitions for us. All probabilities must be between 0 and 1. That's because you can't have something greater than 1 like the chance of it occurring. If something is 1, then it's definitely going to happen. If it's 0, then it's not going to happen. So if the probability of something is 1, then it's certain. If it's 0, it's not going to happen. This here, you can say A naught or A complement. They're the same thing. Sorry, A complement. So if the probability of A happening is a half, then the probability of A not happening is a half because they need to add up to 1. So a better example would probably be if A was a quarter, then A naught or A complement is 1 minus a quarter, which is 3/4. So they must add up to 1. The probability of A or B is a probability of A plus a probability of B minus where they intersect. So I'll show you here. I've got A. There's A, there's B. I'm going to say A is that area there. B is this area here. A or B is everything that's in A, or it's in B, or it's in both. But you can see here that we've doubled up on this area in between. So we add the probability of A, we add the probability of B, and then we subtract this probability in here so that it doesn't double up. And then we'll end up getting the probability of A or B, which is everything inside A or B or both. Two events are mutually exclusive if they don't intersect. So if we drew that, A and B, they wouldn't cross over each other. So the probability of A or B is a probability of A plus a probability of B. You don't need to subtract where they intersect because by definition mutually exclusive means that they don't intersect. Okay, so if I have a card chosen at random from a well-shuffled deck of 52 cards, well-shuffled just means that it's random. So, they're not in any particular order. The probability of getting an ace, the probability of an ace is how many aces are there in the pack? 4. How many cards are there? 52. So it's 1 on 13. The other way you can think about that is you have got 4 different suits. In each suit, there's 13 cards. And out of those 13 cards, one of them is an ace, so it's 1 in 13. Okay, the probability that it's not a heart, so H complement. If the probability of getting a heart is there's 4 suits, it's 1 out of 4. The probability of not getting a heart is 3 out of 4. The probability of getting an ace or a heart, the probability of ace or a heart is the probability of an ace, which we know is 4 in 52. We just worked that out. The probability of getting a heart is 13 on 52 because we've got 13 hearts out of 52 cards. Can I get an ace of hearts? I can. So here I would have included the ace of hearts. Here I would have included the ace of hearts. We can't count it twice, so we've got to subtract 1 on 52 because we've accounted for it here and for here. If I want to know one or the other or both, we need to subtract 1 on 52 because we've accounted for it twice here. So it will be 4 plus 13, which is 17, minus 1 is 16 on 52. Divide everything by 4. We get 4 on 13. Either an ace or a king. So an ace or a king. They don't intersect because you can't get a king of aces or an ace of kings. So we just say the probability of a king plus the probability of an ace. We don't need to subtract where they intersect because they don't occur together. The probability of a king is 4 on 52. Probability of an ace is 4 on 52. Overall, that's 8 on 52. Divide everything by 4. We get 2 on 13. So we've got 1 on 13, 3 on 4, 4 on 13, 2 on 13. Okay, 500 people questioned and classified according to age and whether or not they regularly used social media. So here's less than 25, greater than 25. One of them should be equal to. I guess we could say less than 25 is 24 and up to 25, and greater than 25 is 25 and over. Yes, so they like social media, or no, they don't like, or don't use social media. Okay, one person is selected from the 500. Find the probability that the person regularly uses social media. So regularly uses social media, there's 300 out of 500, which is 3 on 5. So there's a 60% chance they regularly use social media. The person is less than, so the probability that the person is less than 25, I've got 240 people out of 500, so 24 out of 50. Divide them both by 2, I get 12 out of 25. The person is less than 25 years of old and does not regularly use social media. So less than 25 and does not regularly use social media. 40 out of 500, which is, divide them both by 4. No, 10. I get 4 on 50, which is 2 on 25. That's right, isn't it? Yep. Okay. A dartboard consists of a square of length 2 meters. So it's 2 by 2. 1/4 of a circular disc that's supposed to be centered at the bottom left vertex. So here, I've got 1/4 of a circle is of the square as shown. So somehow I deleted this image, but that's shaded. If a dart thrown at the square is equally likely to hit any part of the square and it hits every time, so it can't miss, the probability of hitting the shaded region. So if we think about it, the shaded region is 1/4 of a circle of radius 2, because that's your radius from here to here. So the probability of shaded is the area for a circle is pi r squared, but this is 1/4 of a circle. So 1/4 times pi times 2 squared over the whole shape, which is 4. 1/4 of 2 squared is just 1. So I end up with pi over 4. So a chance of hitting this area is pi over 4. Okay, next we're going to look at Karnaugh maps, which is another way of displaying like a Venn diagram. So I will do it as a Venn diagram as well, over here. Okay, so Simone visits the dentist every 6 months for a checkup. The probability that she'll need her teeth cleaned is 0.35. So I'm going to say here is cleaned, it's 0.35. Probability that she'll need a filling is 0.1. The probability she will need both is 0.05, so 0.05. So that means here is 0.3, here is 0.05. Together, we've got 0.3 plus 0.05 plus 0.05, which is 0.4. So out here must be 0.6. That makes sense. Okay, if we put it into a Karnaugh map or probability table, we know clean and filling is 0.05. We know that the chance of needing a clean is 0.35, the whole thing. The chance of needing a filling is 0.05. So here, the chance of not needing a filling and a clean, and we do need a clean, is 0.3, because acrosswards, like horizontally, they must add to 0.35. Just like vertically, these must add to 0.1, so that's got to be 0.05. Now, acrosswards, horizontally, they have to add to 1. So that's 0.1, that's got to be 0.9. And if this here, downwards, that's got to be 0.6. If we add across horizontally, it's got to be 0.65, which makes sense because 0.35 and 0.65 is 1. Okay, what is the probability that she'll need her teeth cleaned, but will not have her teeth cleaned, but will have a filling? So the probability that she will not have her teeth cleaned, but will have a filling, not have her teeth cleaned, will have a filling, is 0.05. What is the probability that she'll need neither treatment? So she doesn't need cleaning and she doesn't need a filling. No cleaning or filling is 0.6, so 0.60. Now I'm just going to scrub this out and make it clean. Make this a bit smaller. So that's 0.3, 0.6, 0.9, 0.65, 0.05. The reason I did that because this next problem involves that problem and I need to be able to see it. Conditional probability. The outcome of one event is dependent on the previous event. So if I said to you, let's think about it in terms of sport. If someone shoots for goal, the probability of getting a goal might be a half. So the probability of missing is also a half. But if they miss the goal, so if they miss the goal, the probability of getting the next goal might be reduced. So the probability of goal getting that they missed a goal might now be a third. So the probability of getting the next goal is dependent on the previous goal. That's what a dependent event is. Something else we could think of, if I had a pack of cards and I told you to get a king, so the probability of getting a king is 4 in 52. If I don't put the card back into the pack and then I want to find what's a chance of getting another king, that is, there's only 3 kings left and there's only 51 cards. So this probability has affected my next probability. So that means that they are dependent. If I put the card back, they wouldn't affect each other, so then it's independent. What we have here, the outcome of one event is dependent on the previous event. So the probability of B, given that A has occurred, is the probability of both A and B occur over the probability of A occurring. And the probability of A can't be 0. So here, in words, the probability of B happening given that A has happened. For the information, so number 7, for the information in example 6, given that Simone had her teeth cleaned on a particular visit to the dentist, what's the probability she also needed a filling? So what's the probability? She had her teeth cleaned, so given that her teeth were cleaned, what's the probability she also had a filling? So that's the probability of a filling and cleaned over the probability of having them cleaned. Filling and cleaned, we know is filling and cleaned, 0.05. Over the probability of having them cleaned. Probability of having them cleaned is 0.35. In an exam, you can't leave it as 0.05 on 0.35. You must multiply the top by 100, you get 5, and on the bottom, you get 35, which we can simplify to be 1 on 7. You could, of course, do it just by looking at the table. So here, what's the chance of getting her a filling, given that she had her teeth cleaned? So we say here, we know if she had her teeth cleaned, that's here. The probability that she had a filling, given that she had her teeth cleaned, we don't worry about any of this. We know that she's had her teeth cleaned, so it's got to be out of 0.35. The probability that she had a filling and her teeth cleaned is 0.05. So there's our probability of getting a filling and her teeth cleaned, given that she had her teeth cleaned. We divide it by 0.35 because we know that she has had her teeth cleaned, for sure. Okay, here's another given one. So, in a certain town, the probability it rains on Monday is 0.21. So I'm going to say here is Monday. Rain, not rain, 0.21, 0.79. If it rains on Monday, then the probability it rains on Tuesday is 0.83. So this is Tuesday, 0.83, 0.17, rain, not rain. If it doesn't rain on Monday, the probability that it rain on Tuesday is 0.3. So 0.3, rain, 0.7, not rain. What's the probability that it will rain on both Monday and Tuesday. So we've got to have rain and then rain, and they have to occur together. So that will be 0.21 times 0.83, which is 0.1743. Now you could get asked to do this by hand on an exam, so you need to know how to multiply them. Okay, what's the probability that it rains on a Tuesday? So we rain on a Tuesday here. So we get rid of that. Rain on a Tuesday here. And we rain on a Tuesday here. So we say rain, rain, or not rain, rain. So this is one event, this is another, so we add them. These have to occur together, so we multiply them. These have to occur together, so we multiply them. So I've got 0.21 times 0.83 plus 0.79 times 0.3, which is, we already have the last one, so 0.79 times 0.3. If we add them together, 0.4113. Okay, last one. It rains on Monday given that it rained on Tuesday. So the probability that it rains on Monday given that it rained on Tuesday is the probability that it rained on Monday and Tuesday. This is the rule up here. So using this rule, given that it rained on Tuesday. Okay, and if you look up, the probability that it rained on Monday and on Tuesday, we've got up here, 0.1743. The probability that it rained on, given that it rained on Tuesday, the probability that it rained on Tuesday is 0.4113. So, this divided by this. Okay, we'll go to 4 decimal places. It doesn't specify, but generally in an exam they'd say, so 0.4233, I think it was. 48. Okay, so 0.4248. Don't forget to check the question to see how many decimal places. Okay, here's a fun one. A family washing the dishes. Adrian, Regan, Michael are doing the dishes. Since Adrian is the oldest, she washes 40% of the time. So here's Adrian, Regan, Michael, 40%, 30%, 30%. They can. Adrian washes, a probability of at least one dish being broken is 0.01. So breaking a dish, 0.01. Not breaking a dish is 99%, 0.99. Regan breaking a dish is 0.02, which means not breaking a dish is 0.98. And Michael breaking a dish is 0.03, so not breaking a dish is 0.97. Okay, first one, what's the probability that at least one dish will be broken? So we can have Adrian, let's change colors. We can have Adrian washing and breaking a dish, Regan washing and breaking a dish, Michael washing and breaking a dish. So the probability at least one dish broken is 0.4 times 0.01 plus 0.3 times 0.02 plus 0.3 times 0.03, which is 0.0. I've got three numbers after the decimal point, 0.0004, sorry, plus 0.006 plus 0.009, which is 0.019. So that's a chance that at least one dish is broken. Not very high. Given that at least one dish is broken, what is the probability that Michael's washing? So the probability that Michael's washing, given that at least one dish is broken. So that's the probability that Michael is washing and a dish is broken over the probability that at least one dish is broken. Michael washing and a dish broken is 0.3 times 0.03. On the probability of dishes broken, we've got that from the last question, 0.019. On top, I get 0.009, because 0.3 times 0.03, over 0.019. Times them both by 1,000, we get 9 on 19. So the chance of Michael washing, given that we've broken a dish, is nearly a half, which makes sense because he's more than likely than everyone else to break a dish. Okay, as part of a school evaluation of a school canteen, all students in year 10, 11 and 12 are asked to rate the canteen as poor, good or excellent. What's the probability of a student chosen at random from the senior secondary colleges in year 12? So in year 12, we have 80 students out of 400, which is 1 in 5. Is in year 12 and rates the canteen as excellent. Excellent in year 12 is 35 on 400, which is 7 on, how many 5s going to 400? 80. Is in year 12, given that they rated the canteen as excellent. So the probability that they're in year 12, given that they rated the canteen as excellent, is the probability that they're in year 12 and rated it as excellent over the probability, what's C? I think it's canteen. Excellent. That's equal to the probability that they're in year 12 and rated as excellent over the probability that it's rated as excellent, which is in year 12 and excellent. What's in year 12 and excellent? In year 12 and excellent is 35 out of 400 over the probability of excellent. So the number of excellence is 160 on 400. Those 400s will cancel. We can divide the top by 5, we get 7. We can divide the bottom by 5, and we get 32. Another way you can do it is you can say, we know that they rated the canteen as excellent, so we only have 160 people to choose from, of which, it being in year 12 is 35. So it's 35 over 160, which is 7 on 32. It's good to use the rule because you know how to use it when you get into a question that has a harder probability, or a harder way to work it out. It's not in a table. Okay, rated the canteen as excellent given that they're in year 12. So the probability of excellent given they're in year 12 is excellent and year 12 over year 12. Excellent in year 12 we know is 35 on 400. The probability that they're in year 12 is 80 out of 400. 35 out of 80, which is 7 on 16. Okay, independent event. So that's when one event has no effect on another. So let's think of things that are independent. If we were watching the Olympics and what's the guy who runs really fast? Lightning Bolt Hussein. Oh no, I can't remember his name. Usain Bolt. Okay, if I sneeze, what's the chance of Usain Bolt winning the 100 meters? Does my sneezing have any effect on him? No, they're independent of each other. If I pull a ball from a bag which has 10 different colored balls in it, and then I put the ball back in the bag, and then I grab another ball out, does the ball that I got first affect the next one? No, it doesn't. So that's what an independent event is. Now, where does independence come from? If we have the probability of A given B is the probability of A intersects B over the probability of B, if B doesn't affect the outcome of A occurring. So the probability of A given that B occurs, if B occurs and it doesn't affect A, that would just be exactly the same as the probability of A. because B occurring doesn't make any difference to the probability of A occurring. Now, if we know that, the probability of A occurring, because if B occurs, the probability of A given B, if that's just a probability of A because B doesn't have any effect, then we can replace in this rule here, we can say the probability of A is equal to the probability of A intersects B over the probability of B. We can multiply that across and we get the probability of A intersects B is the probability of A times the probability of B if they are independent. So this rule comes about because we know that the probability of A given B is just the probability of A, which means that B has no effect on A. So we can replace this probability of A given B with the probability of A, multiply the probability of B across, and we get the probability of A intersects B is probability of A times the probability of B if they are independent, which means they don't affect each other. So that's where the rule comes from. Okay, so I've got this rule. If you work out a probability, like the probability of A and the probability of B, and the probability of A intersects B, and this rule it holds, like if both sides are equal, then we know that they're independent. If they are independent, to work out their probabilities, we just multiply them together, like if they want to occur at the same time. So the probability that Monica remembers to do her homework is 0.7, while the probability that Patrick remembers to do his is 0.4. If these events are independent, so it doesn't make any, Monica doing hers or not doing it doesn't affect Patrick, and vice versa. So they're not in the same house and they're not affecting each other whether they can do their homework or not. If they lived in the same house and Patrick was Monica's little brother and he would annoy her and stop her from doing her homework, then they would affect each other. But these are two completely different kids. They have no effect on each other. What's the probability that both do their homework? So I want Monica to do her homework and Patrick to do his. Monica's 0.7, Patrick is 0.4. So there's a 0.28 chance that they will both do their homework. What's the probability that Monica will do hers and Patrick forgets? That's Monica times Patrick forgetting, which is 0.42. So there's more chance that Monica will do hers and Patrick won't than both of them doing it. Now, I didn't put in this question, but what's the probability that either of them do it? No. If I said at least one of them do it. At least one. So we could have Monica doing it and Patrick not. We could have Patrick doing it and Monica not, or they could both do it. So if Monica does it and Patrick doesn't, we know that's 0.42. If Patrick does it, which is 0.4, and Monica doesn't, that's 0.12. If they both do it, it's 0.28. So we know that is 0.82. But another way that we could work it out, if it's at least one, we could say that's also the probability 1 minus the probability that neither of them do it. So Monica doesn't do it and Patrick doesn't do it. If Monica doesn't do it, it's 0.3. If Patrick doesn't do it, it's 0.6. I forgot to put the 1 minus at the front. 1 minus 0.3 times 0.6, which is 1 minus 0.18, which is 0.82. It's exactly the same answer. Okay, so don't forget you can use complements or symmetry to work out solutions. Okay, discrete random variables. So this is usually looking at displaying all of the outcomes in a table and then finding out certain probabilities. What's a probability that if a ball is drawn 3 times from a jar containing 4 white, 6 black balls with replacement, a white ball will be drawn exactly once? Okay, so the probability of a white ball is 0.4. The probability of a black ball is 0.6, and it's going to be the same every time because they're replaced. So if I want to get a white ball exactly once, I could get white, black, black. I could get black, white, black. or I could get black, black, white. They're all exactly the same probabilities. So I've got 3 times a white ball, which is 0.4, a black ball, which is 0.6, and a black ball, which is 0.6. What have we got? We've got 0.6 times 0.6, which is 0.36, times 0.4, which is 0.144, times 3, which is 0.288, is that 0.432? Let's just check. Oops. 3 times 0.6 times 0.6 times 0.4, 0.432. Okay, so that's a chance of getting only one white ball. So you have to work out the different combinations that can occur. There's 3 different ways. Later on, we'll learn something called binomial distribution, where we can do that a lot faster. Consider the table shown. Does this meet the conditions for a discrete probability distribution? Are all of the probabilities greater than 0 and less than 1? Yes. Do all of the probabilities, probability of x equals 0 plus the probability that x equals 1 plus the probability that x equals 2 plus the probability that x equals 3, do they all add up to 1? 0.2 plus 0.3 plus 0.1 plus 0.4, it adds to 1. So yes, it's a probability distribution. Use the table to find the probability that x is less than or equal to 2. So it can include 2, so we just add these values up. So probability that x is less than or equal to 2 is 0.2 plus 0.3 plus 0.1, which is 0.6. Of course, probability that x is less than or equal to 2, in this case, is also 1 minus the probability that x equals 3. So we can use this, 1 minus 0.4, which is 0.6. So don't be afraid to use symmetry. Generally, it can help you solve questions a lot faster. Let x be the number of heads showing when a fair coin is tossed 3 times. Find the probability distribution of x and show the probability sum to 1. So, how many heads can we get when we toss a coin 3 times? We can get none, 1, 2, or 3. So that's x, and these are the probabilities. So if I get no heads, I've got to get tail, 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 which is a half times a half times a half, which is an eighth. If I get one tail, I can get tail, head, 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 tail, head, 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 tail. So that's 3 times a half times a half times a half, which is 3/8. 2 tails is the same, 3/8. 3 heads, sorry, head, 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 is a half times, I just stuffed that up before. They are both the same. So if I get 2 heads, that's 1, 2, 3. So that's 3/8. If I get 1 head, it's exactly the same. There's 3 outcomes. Getting 3 heads, half times a half times a half, which is an eighth. So there's our probability distribution. If I add up the probabilities, I get 1 on 8 plus 3 on 8 plus 3 on 8 plus 1 on 8, which is 8 on 8, which equals 1. So there, the probabilities add to 1. Find the probability that 1 or more heads shows. So the probability that x is greater than or equal to 1 is 3 on 8 plus 3 on 8 plus 1 on 8, which is 7 on 8. Of course, it's much easier to do 1 minus the probability that x equals 0, so no heads. 1 minus 1 on 8, which is 7 on 8. Find the probability that more than one head shows, so we can't include 1, so that just means this bit here, so more than 1. That's the same as the probability that x is greater than or equal to 2, which we know is 3/8 plus 1/8, which is 1/2. Okay, here's a pretty cool question. An experiment consists of tossing an unbiased coin and tossing it again if and only if the first toss yielded a head, and then tossing it again if and only if the second toss yielded a head. Draw a tree diagram. So I have head, tail, that's a half, half. Here we stop. If I get a head, I toss it again, head, tail, half, half. If I get a tail, I stop, toss it again. I can get a head or a tail, half, half, and we stop here no matter what. If X denotes the total number of heads obtained, draw up a probability distribution table. So here I get no heads. Here I get one head. If I follow this path, I get 1, 2 heads. If I follow this path, I get 3 heads. And my probabilities are 0 heads is a half. A head and a tail is a half times a half, which is a quarter. Head, head, tail is 1 on 2, 1 on 2, 1 on 2, which is 1 on 8. And then head, head, head is a half times a half times a half, which is also 1 on 8. I've got a half plus a quarter plus an eighth plus an eighth, which is 1. So it's a probability distribution table. Okay, the random variable x represents the number of chocolate chips in a certain brand of biscuit. It's known to have the following distribution. So 2 chocolate chips is a 1%, 3 it's 25%, 4 40%, etc., etc. The probability that x is greater than or equal to 4, we can add all of them up, or we can do 1 minus the probability that x equals 2 minus the probability that x equals 3, which is 1 minus 0.01 minus 0.25, which is 0.74. So there's a 74% chance that we get at least 4 chocolate chips. The probability that x is greater than or equal to 4, given that it's greater than or equal to 2. So by the rule, greater than or equal to 4, given, instead of saying x is greater than 2, I'm going to say x is greater than or equal to 3, because it includes 3. That's the probability that x is greater than or equal to 4, intersecting x is greater than or equal to 3, over the probability that x is greater than or equal to 3. Now, if you're not sure on the intersection, draw a number line. There's 4, there's 3. Greater than or equal to 3 is there. Greater than or equal to 4 is there. Where do they intersect? From 4 onwards. So here, it's the probability that x is greater than or equal to 4 over the probability that x is greater than or equal to 3. Greater than or equal to 4, we already worked out, is 0.74. Greater than or equal to 3 is all of this, but it's also 1 minus 0.2. 1 minus 2, which is 0.01. So I get 0.74 over 0.99, which is 74 on 99. Okay, the probability that x is less than 5, so I'm going to rewrite that as the probability that x is less than or equal to 4, because we don't include 5. Given x is greater than 2, that's the same as x is greater than or equal to 3. We need to find, that's equal to the probability that x is less than or equal to 4, intersecting x is greater than or equal to 3, over the probability that x is greater than or equal to 3. If we want to find where they intersect, number line, greater than or equal to 3, less than or equal to 4. So I've got the probability that 3 is less than x, which is less than 4, over the probability that x is greater than or equal to 3. Okay, 3 and 4, if we add them together, we get 0.65. Over the probability that x is greater than or equal to 3, we know is 0.99. So our answer is 65 on 99. So it's a good thing to do to draw these number lines, because then you make sure you don't stuff up anything. And also, if you get greater than, go up to the next number and put it equal to, so that you include that value, so you don't get confused. This expected value on mean sometimes is a little bit of a, not a shock, but it's a little bit confusing for people, because when you have expected value, you can have numbers greater than 1. Expected value isn't actually a probability, it's the number of times you expect something to occur. For an example, if I had a coin and I tossed it 3 times and I said to you, how many heads would I expect to get? Well, you know, each time there's a half a chance you're going to get a head, and you've got 3 times, so 3 times a half is 1.5. So if I toss a coin 3 times, and each toss I have a half a chance of getting a head, I've got a half plus a half plus a half, which is 1.5. I expect to get 1.5 heads out of 3 if I toss a coin 3 times. So it's not my probability, it's just your expected number of outcomes, or your average, or your mean. The average number of heads if I toss it 3 times is 1.5. How does this apply to problems? Here, I've got a person may buy a lucky ticket for $1. They've got a 20% chance of winning a $2 prize, 5% chance of winning an $11 prize, otherwise they lose. So I'm going to set up a table. We've got 3 outcomes. They buy a ticket for $1. They've got a 20% chance of winning a $2 prize. So they don't really win $2. They actually win 1 because they paid $1 for the ticket. That happens 20% of the time. A 5% chance of winning an $11 prize, which is really $10 because they had to pay $1 for it. So that's 0.05. And we have got, otherwise they lose. So they lose $1, and that is 75% of the time. Now you might say, hang on a sec, I've got a negative value here. You can't have negative probabilities, but you can actually have negative outcomes, like negative events. Now, if I want to work out the expected value, it's the sum of all x, which is these values, times their probabilities. So we multiply these 2 values together, and then we add them. So my expected value, or my mean, also given by mu, is -1 times 0.75 plus 10 times 0.05 plus 1 times 0.20, which is -0.75 plus 0.50 plus 0.2, which ends up -0.05. So what does that mean? It means that every time I play this game, I'm going to lose 5 cents. Or the person who's running the game, they make 5 cents. Hope they don't spend it all at once. It's not a very enticing game for either people. You don't really take on a massive chance, and you don't really lose much. So I guess it's for people who don't like the excitement of betting. They've got a chance of winning a little bit, but not much chance. Okay, a coin is biased in favor of head, so they're probably obtaining a head on any single toss is 0.6. The coin is tossed 3 times. If x is the number of heads obtained, find the expected value. Okay, so let's have a look at this one. We've got a coin that we toss. We toss it 3 times. We can have 0 heads, 1 head, 2 heads, 3 heads. And these are their probabilities. Now, it's not your normal probability, because if I get 0 heads, I must get all tails, which is 0.4 to the power of 3, because it's not a 50-50 chance. 0.4 to the power of 3 is 0.064. If I get 1 head, that's 0.6, and then I must get 2 tails, so 0.4 times 0.4. That can occur 3 times. We've done this a few times. So 0.6 times 0.4 is 0.24. Times 0.4 is 0.96. Times 3 is 0.288. 2 heads, I can get 0.6 times 0.6 times 0.4, because I get head, head, tail. Of course, that can be arranged 3 different ways, so times it by 3. So I've got 36.36 times 0.4, 1.44, times 0.3, which is 0.432, Lastly, we've got 3 heads, which is 0.6 to the power of 3, 0.216. Okay, my expected value is x times the probability. So I don't really need to write this, but 0 times 0.064 plus 1 times 0.288 plus 2 times 0.432 plus 3 times 0.216. Okay, so we get 0.288 plus 0.864 plus 3 times 0.216, 0.648. Okay, if we add them together, what do we get? 1. We get 1.8, which makes sense because we've got 3 coins, we toss it 3 times, and each coin, each time the chance of getting a head is 0.6. 3 times 0.6 is 1.8. So expected number of heads when I toss a coin that's biased towards heads of 0.6, you expect to get 1.8 heads if you toss it 3 times. Okay, here's a rule. It's on the formula sheet. You need to, I just buggered this up. It doesn't matter. You need to know the rule, but you don't actually need to really understand it because they don't, like I've never seen them actually ask something on these questions. If I said to you, what's the expected value of something times x plus another value? That's exactly the same as that value multiplying by the mean plus that value. So here, in example 18, our expected value was 1.8. Stuff that up. So here, e of 3x plus 1, by this rule up here, that's the same as 3 times e of x plus 1, which is 3 times 1.8 plus 1, 5.4 plus 1, which is 6.4. The next one, e of x squared. Now this rule doesn't tell us how we would do this really, but what it is, if we've got e of x squared, if we know e of x is the sum of all x times the probability of x, then e of x squared is the sum of all x squared times the probability of x. So in this case here, we have to work out this value, we have to work out this value squared times its probability. So e of x squared, I'm not going to bother with this because 0 squared times that is still 0. 1 squared times 0.288 plus 2 squared times 0.432 plus 3 squared times 0.216. Now I can't really be bothered working this out by hand. So I've got 1 times, what was it? 0.288 plus 2 squared times 0.432 plus 3 squared times 0.216, which is 3.96. So e of x squared is 3.96. Now you need to remember how to work that out because we use that later on for variance. We're pretty close to the end, which is good. I've been talking for way too long. Okay, here's another one for expected value. For a $5 monthly fee, a TV repairman guarantees customers a complete service. He estimates the probability that a customer will require 1 service call a month is 5%. The probability that requires 2 calls is 1%. The probability 3 or more calls is 0. So obviously we don't need to do the 0 one, the 3 or more calls. So we could have, I'll put into 3 levels. This one's the calls, this one's the cost, and this one's the probability. X equals the calls. So I can have 0 calls, 1 call or 2 call. If I have 0 calls, I make $5. I don't need the dollar sign. If I have 1 call, each call costs a repair company $40. So I've made $5 off the person, but then I have to pay $40 out to get someone out there. So I'm going to lose $35. The chance of 2 calls is 0.01. If I have 2 calls, it's going to cost me $40 for the first, $40 for the second, and the people are paid $5. So in this case, I lose $75. The chance of losing $75 is 0.01. The chance of losing $35 is 0.05. The chance of gaining $5 is 0.94 because it's 1 minus those two. My expected value is the amount of money I make times its probability. So 5 times 0.94 plus negative 35 times 0.05 plus negative 75 times 0.01. 5 nines are 45 and 20 is $4.70 minus 35 times 0.05, $1.75 minus, that's 75 cents, so 0.75. So I've got 470 minus 250, which is $2.20. So each time they sell this insurance, whatever it is, they make $2.20 per person on average. So if you're a good salesman, if you sell like, I don't know, a couple of hundred of these a month, and those people keep paying $5 a month, if you made $2.20 for each one, eventually the company's going to start making big money. Because each $5 that they get to keep $2.20 of it, and the rest of it's paid out. Okay. So we know our mean. Now we have to work out variance, which is how far your data spreads out. So if I said to you on a test, the average score is 80, the highest score is 100, and then the lowest score is 60. It's not too far spread out. But if I said to you the test, the average was 50, and the maximum is 100, and the minimum 0, this has a higher variance because the scores spread out more than this one does. So variance and standard deviation are looking at how far data is spread out. Okay, here to find the mean, we know that our mean is E of x, which is also mu. It's the sum of all x times the probability of x. So 0 times 0.2 plus 1 times 0.3 plus 2 times 0.5, which is 0.31, 1.3. The variance. To find the variance, we need to use E of x squared minus E of x all squared. Now we've got E of x, that's what we just found down here. We've got to find E of x squared. So E of x squared is 0 squared times 0.2, which is nothing, 1 squared times 0.3, plus 2 squared, that's not squared, times 0.5. So I have 1 times 0.3, 0.3, plus 2 squared times 0.5, so 4 times 0.5, which is 2, so it's 2.3. Therefore, my variance is E of x squared, 2.3, minus E of x all squared, so that's E of x, 1.3 squared, 2.3 minus 1.69. What is that, 0.31? 0.61. 2.3, let's have a look. 2.3 minus 1.69 is 0.61. Then to find the standard deviation, we've got to square root that. Just stuff that up. So 0.61, 0.7810. So the standard deviation of x is the square root of the variance of x, which we know is the square root of 0.61, which we said is 0.7801. Open back up. 0.7810. So that is our variance, our standard deviation, and our mean. Now, the variance of ax plus b, so a linear combination of the variance, you just follow the rule. So if I've got ax plus b, it's just a squared times the variance. So here, if I have a random variable such that the variance of x is 9, what's the variance of 3x plus 2? Well, by the rule, it's 3 squared times the variance of x, which is 9 times 9, which is 81. What's the variance of negative x? Once again, by the rule, it's negative 1 squared times the variance of x, which of course is just the variance of x, which is 9. Okay, last thing, the number of chocolate bars sold by a manufacturer in any month has the following distribution. So if I sell 100, it does 5%, 150, 15%, 200, 35%, etc. What's mu minus 2 sigma is less than or equal to x, which is less than or equal to mu plus 2 sigma. So don't forget, mu is expected value. Sigma is the standard deviation of x, which is the square root of the variance of x. So what we need to do first is find the expected value. We know e of x is that number times that number, and then we add them all up. So 100 times 5, 150 times 0.15. I've worked this out before. I think it's 225. So let's try it. 100 times 0.05 plus 150 times 0.15. Of course, it's easier for you because you can just have your calculator. 200 times 0.35. 250 times 0.25. 300 times 0.15. 400 times 0.05. I've got a plus there. So 400. It is 225. So that's e of x, 225. We next need to find e of x squared. Now, because we've got this in our calculator from before, select all, paste, edit, select all, edit, copy, edit, paste. Now, when I want to find the square of all these, I just simply put in a squared, 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 squared. I think it's 55,000 it is. Just off the top of my head. Okay, so e of x squared is 55,000. We know the variance of x is e of x squared minus e of x all squared. So it's 55,000 minus 225 squared. I think it's 4375. 50,000 minus 225 squared. That's not right. 55,000. 4375. So that's my variance. So my standard deviation is the square root of 4375. So we square root that. 66.14. Okay, now we want to work out the probability that mu minus 2 sigma. So let's say mu minus 2 sigma. What is that? Mu is 225 minus 66.14. And then I want to work out mu plus 2 sigma, which is 225. That's 2 times minus 2 sigma, 66.14. Okay, so let's go 225. Don't know why I didn't just write it. 225 minus 2 times that value. And then do exactly the same thing, but this time with plus. Okay, so 92.7 to 357.3. Probability 92.7 is less than or equal to x, which is less than or equal to 357.3. Now, we only have discrete values, so we're going to have to round this one up. So that's the probability that 100 is less than or equal to x, which is less than or equal to, this one we're going to have to round down because it doesn't include 400, so 300. Now, if I want that probability, 100 is less than x, which is less than 300. We want to add this, this, or we can do 1 minus the probability that x equals 400. The probability that x equals 400 is 0.05, so 1 minus 0.05, which is 95. So there's a 95% chance that if I go from my mean take away 2 standard deviations and my mean add 2 standard deviations, so if I go 2 standard deviations to the left and 2 standard deviations to the right off the mean, there's a 95% chance that I'm going to use this amount of chocolates in a week. So between 100 and 300 chocolates bars, there's a 95% confidence that I can say that I'll sell between 100 and 300 in a week. So if you were to have at least 100 and less than 300, there'd be a 95% chance that you would have enough to sell between 100 and 300. That's a confidence interval. Eventually we have a look and we say the probability that mu minus sigma, 1 standard deviation, is less than x, which is less than, actually I can't do it there. Eventually we do confidence intervals. If you say mu plus or minus 1 standard deviation, 68% of data occurs in there, in general, not always the case. Mu plus or minus 2 sigma, 95% of data occurs in there. And if you do mu plus or minus 3 sigma, so if you go 3 standard deviations out, 0.997, so 99.7% of data will occur within plus or minus 3 standard deviations. Okay, so hopefully I've given you an idea of how to complete Chapter 4.13. If you have any questions, you can also ask me. Hopefully that wasn't too boring. I tried to go through it as quick as I can, so you can always rewind it if you need to. If not, good luck finishing